So this is our fourth look at proton NMR. We're going to have a look at splitting patterns now. We'll also touch again on integral and chemical shift, but the main thing we're interested in today is the splitting patterns. And I said here that peaks are split by the influence of adjacent or next door hydrogens. We need to be aware of a couple of of some of the key terms here before we look at that. We call a peak that hasn't been split, so just a single peak, a single line, a singlet. If that peak has been split into two lines, we call it a doublet. If it has been split into three lines, we call it a triplet, and the peaks will be in the relative heights of 1 to 2 to 1 here. And then if it's split into 4, we say that's a quartet, and that will be in the relative order of 1 to 3 to 3 to 1. These will often have abbreviations of S, D, T and Q. There are more than that, but as far as A level is concerned, we don't really need to worry about those. So anything beyond that, we're just going to call a multiplet, and we'll see some examples of those as we go along. We also need to be aware of something called the N+1 rule. And that states that the N is the number of hydrogens in the adjacent environment. All of this makes much more sense, I think, if we actually have a look at some examples. So let's have a look at what we would expect the splitting to look like for a really straightforward compound, ethanol, and it also allows us to think about the OH peak there. So we would expect to see 3 peaks on our NMR spectrum. They would have the relative peak heights or integral of 3H, 2H and 1H. Remember that the integral, and I'll just label this here, the integral tells us the number of hydrogens that are in that environment. It doesn't tell us about the splitting pattern, and that's where I think people sometimes get a bit confused. So if we have a look at, and we'll call this one environment A, environment B and environment C. If we have a look at environment A, it is adjacent to environment B, next to environment B. Environment B has 2 hydrogens in it. So what we would say here is this peak is split by 2 times hydrogens in the adjacent environment B. So according to the N+1 rule, that is therefore 2 plus 1 equals 3. So we would expect this 3H peak to be split into a triplet. Notice the fact that this is a 3H environment and the fact that this has been split into a triplet is not related to each other. The fact that this peak, A's peak, has been split into a triplet is related to the fact that there are 2 hydrogens in environment B, and the N+1 rule saying that this peak will be split by this environment into a triplet. If we have a look at environment B, or the peak is split by 3 times hydrogens in the adjacent environment A. There is another environment adjacent to it, which is the one on the OH, on the alcoholic environment. However, these don't have any influence on splitting. They don't couple, that's the term we use. So they don't couple with this one. So we ignore this. So the peak is split by the adjacent environment A. OH have no impact. And therefore, what we're expecting to see is this peak split into 3 plus 1 equals 4 equals a quartet. Now, environment C, the 1H environment, there is no coupling because it is an OH environment, and OH environments don't couple, so therefore no splitting. So according to the N+1 rule, there's no adjacent environments. 0 plus 1 equals 1, therefore we'd expect this to be a singlet. It's going to be, we're actually going to have a look at some real spectra now. So let's have a look at this spectrum first of all. Before we actually start trying to work out what's happening in the spectrum, I think it might be worth us actually predicting what we're expecting to see first of all. So if we have a look at this structure, we've got a hydrogen environment here, which we'll call environment A. Remember, it's that OH environment. It's not even if it was adjacent to anything, it's not going to have any splitting. It's not going to couple. There's no hydrogens on here because that's a double bond. There are going to be two hydrogens on here, which we'll call, sorry about that, two hydrogens on here, which we'll call environment B. And then if we have a look here, there's no hydrogens on here, but there are 3 methyl groups. And because of the rotation around here, these 3 methyl groups are all equivalent. So all of these we will call environment C. So in terms of the integral, in terms of the peak height, we would expect C to have a relative peak height or integral of 9, B to have a relative peak height of 2 hydrogens, and C to have an integral or relative peak height of 1 hydrogen. Let's now think about their splitting. Environment A, there's nothing adjacent to it, and it's an OH anyway on a carboxylic acid, so there's going to be no splitting. So for A, 0 plus 1, we'd expect that to be a singlet. Environment B, let's look at the adjacent carbons. There's a carbon there, there's no hydrogens on it. There's a carbon here, there's no hydrogens on it. Therefore B, we are also expecting to be a singlet. There's no adjacent hydrogens coupling to it. 0 plus 1 means we're expecting it to be a singlet. Environment C, if we look at the adjacent carbon, there's no hydrogens on there. Therefore we're also expecting this to be a singlet. And that's exactly what we see on the spectrum. We've got the acidic OH up here, so that's environment C. This huge singlet here is going to be environment C, and this singlet here is going to be environment B. Although we haven't got an integrator value on here, we can see very clearly that this is significantly bigger than this. So let's have a look at this second environment, second compound here. You might not be able to see it very well, but there's 1.0 and 1.0 over there. That's just that integrated trace telling us that it's got 1 hydrogen in the environment. Here's our molecule. We've got a hydrogen here and a hydrogen here. They're not equivalent hydrogens because of these different groups on here. So let's call this one environment A and this one environment B. So environment A is adjacent to B. B is a 1 hydrogen environment. So we're expecting the signal for A to be split into a 1 plus 1, 2 is a doublet. Let's have a look. Environment B is adjacent to environment A. Environment A is a 1H environment. So we're expecting this 1 plus 1 to split both of these signals into doublets. We could use our understanding about de-shielding to predict which one's going to be which. Chlorine is more electronegative than bromine, so this hydrogen is going to be more de-shielded than this one. So if it's the more de-shielded one is going to be further downfield, so it's likely that this one is going to be environment A and this one is going to be environment B. Butane. From this point on, if you want to pause the video and have a go at maybe predicting some of them yourselves, and then I'll go and then restart the video, and you can and listen to how I've explained it. So butane, we're going to need to draw the structure first of all. So there's our structure. First thing to note is we've got a line of symmetry down here. So these environments here and these environments here are equivalent. So we're going to call this environment A and this environment B. Notice we've got an integrated trace here of 3 to 2. 6 in environment A, 4 in environment B. So the smallest ratio there is 3 to 2. That explains it. So we can automatically predict environment A as being the 3 hydrogen environment, and environment B being the 2 hydrogen environment. But let's explain the splitting. We've got a quartet here and we've got a triplet here. Let's have a look at environment A. A is adjacent to B, and B is a 2 hydrogen environment. So the trace from A is going to be split into 2 plus 1 equals 3, a triplet. Is that what we see on our spectrum? Yes, it is. B is adjacent to A. A is a 3 hydrogen environment. 3 plus 1 equals 4 is a quartet. Do we see that on our spectrum? Yes, we do. So that is indeed correct. So this compound here, butan 2-one. So it's a ketone. So let's predict our spectrum. First of all, let's look at the number of hydrogens in each environment. So this is an environment, we'll call that A. There's no hydrogens on here. This is an environment, we'll call that B. And this is an environment, we'll call that C. So A is adjacent to 0 hydrogens. There's no hydrogens on here, therefore 0 plus 1 equals 1. We're expecting that to be a singlet. B is adjacent to environment C. Environment C is a 3 hydrogen environment. 3 plus 1 equals 4 is a quartet, and C is adjacent to environment B. Environment B is a 2 hydrogen environment. 1, 2, 2 plus 1, 3. We're expecting that to be a triplet. So let's have a look at our spectrum. Very big singlet here. So that's going to be environment A. Environment B we predicted to be a quartet. So that's going to be this one here. Environment C we predicted to be a triplet. That one, yes, environment C. So that's going to be environment C here. Let's also think about, does that make sense in terms of our understanding of chemical shift? Environment A and environment B are closer to the electron withdrawing carbonyl group. So we've got the electronegative oxygen atom here that's going to be pulling electron density off of the carbon and therefore de-shielding this and de-shielding this. Indeed, we find both of these peaks are further downfield compared to environment C, which is further away from this impact, although it still has been de-shielded to some extent. So, propanoic acid. Label our environments A, B, C. A, hopefully we can realise now, A is not adjacent to any other hydrogens, so therefore A is going to be 0 plus 1 is a singlet, which must be this one here. Also, it's very, very downfield. It's exactly where we expect to see the hydrogen from a carboxylic acid. Environment B is adjacent to environment C. So 3 plus 1 equals 4 is a quartet. So C is a 4 hydrogen environment. So we're expecting B to be a quartet. Environment C is adjacent to environment B. Environment B has 2 hydrogens in it. 2 plus 1 equals 3 is a triplet. So our triplet, which we can see for environment C, 1, 2, 3, that's environment C. And then you can just about see on here that there's 1, 2, 3, 4 peaks for the quartet here. There are some effects which we're not going to go into about why these, if you look at these particular peaks here, there's some differences in what we'd expect them to be. In an idealised world they look like that, but that is due to the other effects that we're not going to go into. So if we have a look at this compound here, so this is an ester, methylpropanoate. Let's do the same thing again. Environment A, environment B, environment C. Environment A is not adjacent to any other hydrogens, so 0 plus 1 equals 1. We're expecting A to be a singlet. Environment B is adjacent to environment C. In environment C there are 3 hydrogens, so 3 plus 1 equals 4. We're expecting environment B to be a quartet. And environment C is adjacent to environment B. There are 2 hydrogens in environment B. 2 plus 1 equals 3, triplet. So we're expecting to see environment C as a triplet. 1, 2, 3, that's right. Environment B is a quartet. There's a quartet there, 1, 2, 3, 4. So that's environment B. And then environment A is this singlet over here. Again, let's check that makes sense in terms of our understanding of the de-shielding effects of electronegative atoms. This methyl group here is adjacent to an oxygen, ester grouping as well. So this is going to have electron density withdrawn off of it. Indeed, we see that the peak for A has been pulled downfield away from 0, therefore it's been de-shielded, as has B. And then C, which is further away from the electron withdrawing group, is less de-shielded and is closer to 0. Pentan 3-one. We need to draw the structure first of all. So, before we start, recognise that there is a axis of symmetry here. So this environment and that environment are equivalent. So A, B. So there are only 2 environments, 6 to 4. The smallest ratio is 3 to 2. So instantly we can identify these as environments A and B based simply on the integrated traces. However, let's explain the splitting. So environment A is adjacent to environment B. There are 2 hydrogens in environment A. So environment A we're expecting to see split in a 2 plus 1 equals triplet. And environment B is adjacent to environment A, which we are expecting to see split from these 3 hydrogens here. So 3 plus 1 equals 4, quartet. Do we see that? Environment B is 1, 2, 3, 4. It is indeed, it's a quartet. Environment A, 1, 2, 3, triplet. Again, there's some effect going on here where the heights of these lines have been affected. Again, that's not something we're going to go into today. This example here, let's work out our hydrogen environment. Environment A, because of the rotation around this bond here, these are going to be equivalent. And don't forget also there is a hydrogen on here, and we'll call that environment C. Environment A is stuck out on its own. It's got no adjacent carbon atoms to it. So 0 plus 1, we're expecting to see that as a singlet. Environment B has only got 1 hydrogen, environment C, adjacent to it. So B, I'm going to write that down because it's so a little bit clearer. So B is adjacent to environment C. Environment C is a 1 hydrogen environment, so we're expecting this to be 1 plus 1 equals 2, a doublet. Environment C is adjacent to environment B. There are 1, 2, 3, 4, 5, 6 hydrogens in here. So we're expecting this to be 6 plus 1 equals 7, and we're expecting that to be a multiplet. Do we see that? So we've got a doublet here, so that must be environment B. We've got a singlet here, that must be environment A, and we've got a multiplet there, and you can just about make out the 7 peaks in there, which is environment C. Okay, right. This last one is probably beyond what we'd be expected to do at A level, but it's a nice one to have a look at. Heptan 2-one. So I'm going to draw the structure out. Okay, so we can actually use our understanding of the integrated traces and of de-shielding and the splitting patterns on here, but again this is way beyond what we'd expect to necessarily have to do at A level. So let's label our environments first of all. A, B, C, D, E. I do realise I've just left off a carbon off of here, so I've changed that to CH2. 1, 2, 3, 4, 5, 6, 7. Right, that's right. And does that tally with the number of environments first of all? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's correct. Let's have a look at the integrated traces. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that the number of hydrogens you've got? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the integrated traces match up with that. Let's look at the ones at the extreme ends first of all, because they're probably going to be the easiest to explain. Environment A is not adjacent to anything, so environment A we're expecting to be a singlet. 0 plus 1 equals 1, a singlet. Environment F over here is adjacent to environment E. Environment E is a 2 hydrogen environment, so we're expecting F to be a triplet. So let's have a look just on our spectrum before we move on and say for our 2 3 hydrogen environments, so CH3 here and CH3, have we got a singlet and a triplet? Yes, we have. We've got a singlet here, so that must be environment A, and we've got a triplet here, that must be environment F. So let's have a look at trying to predict the other ones. Environment B, these ones are going to be difficult because we've got carbons on both sides and we haven't really encountered that yet. But environment B has only got hydrogens on one side of it. So environment B is adjacent to environment C. There's 2 hydrogens in environment C, so 2 plus 1 equals 3, which is a triplet. Now beyond that, it gets more complicated, and there are ways we can explain it, but because environment C is adjacent to D and B, then its signal is simply going to be a multiplet. D is adjacent to E and C, again its signal is going to be a multiplet, and E is adjacent to F on one side and D on the other is going to be a multiplet. It's not correct to say that there's 3 here and there's 2 here, therefore it must be n plus 1, so 5 plus 1 equals 6. That is incorrect. There are other factors that are going to take place. So what we can then do is actually use our understanding of de-shielding to try and predict the rest of them. So we've identified our 3H peaks. B we've said is going to be a triplet, all the others are going to be multiplets, and that is over here. And that makes sense in terms of de-shielding. Environment B is really close to the electron withdrawing, the electronegative oxygen, so it's going to be de-shielded. It's moved the furthest downfield. Then if we just look, each of these are getting progressively further away from the electron withdrawing carbonyl there, so therefore they are going to be increasingly shielded. So E is likely to be this one here, D is going to be this one here, and then C is going to be this one here. And that's all. Thank you very much.